Right, hello. In case you haven't seen me yet, I'm David, coordinator of the Maths Learning Centre. If you're watching Engineering Maths IIA, you should have seen me by now. Or you're brilliant, you don't need me, but then you should have seen me anyway because I could have helped you still do better. So anyway, that's enough of my face for today. Right, so this is Engineering Maths IIA revision seminar. And I'm going to talk about the statistics part of the course. And probability. I make no promises to cover absolutely everything. That's not the purpose of these revision seminars. The idea is to organise things in a format that hopefully is helpful for study for this course and give people a chance to ask me questions. Be aware I'm not the lecturer, I didn't write the exam, I'm not involved in your course. But what I do have is lots of experience helping students learning these things. So I have a chance of being helpful. Okay, your statistics and probability lecturer works quite hard to make things understandable, and I'm not going to deny that that is the truth. However, statistics is one of those things that usually requires you to talk about it to somebody. At the very least, the regression is usually the sort of thing that people have to talk to someone about. So I'm just going to do a couple of things. I'm going to go over to the built-in computer. And find a specific thing in your lecture notes. Thank you to the student who sent these to me. I am most grateful because I don't have access to your My Uni course, so I can't see these things. There's, oh, come on. Wrong thing. That's Titch, by the way. If you unfocus your eyes, you can make him look 3D if you want. But I'm... Let's try again. Otherwise, I just... This lecture is cursed, it appears. All right, I can fix this. I do actually have it, I just need to go onto this computer instead. There we go. There, okay. This is the first thing I wanted to talk about. In the past, the lecturer has said that they will put this on the formula sheet in your exam. Is this the truth? Okay, good. This is a summary of the different flavours of hypothesis testing and confidence intervals that you have been shown in this course. And it gives you all the information you need. It's slide 201 in your lecture slides for statistics. And it's also going to appear on your formula sheet. Right, what I want to talk about is how you might organise this information in your head. You have it nicely organised on the page so that you can make sense of it and so that when you get to the exam you'll be able to use this information. Right, so what we have is multiple different hypothesis tests / confidence intervals which come up in various different contexts. And each of them is designed to answer certain questions using certain kinds of data. And the decision of which one to use is based on the kind of question you are trying to answer and the kind of data you have and how the data is set up. And I'm going to talk through these so that I'm going to talk through these and help you hopefully to be able to distinguish between them and to know when to use them, because I think that's the most important thing that I can help with. The actual details of exactly what to do in any given situation and the MATLAB code will be embedded in your notes somewhere, and my major recommendation is to make a similar table to this with the MATLAB code / output that goes with these things. So I would almost literally print out the lecture slides and rearrange them. Pull out the bits that you want and put them into an order that makes more sense to you. That's my first piece of advice on that. Okay, and that's really just me bluffing until I come up with something in my head that I want to do. So I'm just going to so that I can have them both up there at once. The computer is, the recording is recording the document camera, as far as I know. Yes, and I've got the other, that list on the other screen. Okay. The first thing I want to say is that the pieces of information that go together to choose which statistics goes with what are the types of variables involved and how they're related to each other and how the data is set up. So here is how I organise this. I don't know if your lecturer talked about types of variables at all, but I am going to because it's how I organise this information. There are two main types of variables, and they are categorical, which put things in categories, like boxes that I can put things in, like male and female, or before and after, or with the special concrete treatment or without, or I don't know, the particular design for this, for particular design for your paper aeroplane, or whether it's using hard or soft fabric or whatever. It's things in categories. And then there's also quantitative variables, which I draw as a scale, which would be like my x or y axis in a graph. These are the symbols that I have for them. Categorical variables, categories. And quantitative variables are numbers. Okay. The important thing is that sometimes the categories are listed as numbers, group 1 and group 2. But if those numbers, to subtract them to figure out how far apart they are, if that is meaningful, then it's really a number. But if the distance between them isn't meaningful, then it's not really a number. So if it's group 1 and group 2, well, you could just as easily have called them group 2 and group 1, and group 2 is not one more than group 1, it's just different to group 1. So that's how to tell the difference between a category and a number. Okay, and how your variables are related to each other is how we're going to make the decision of what stats goes with what. So most of your questions will be able to be about the relationship between two variables. And they may also just be about a single variable, but I'll do the relationships first. You may be interested in how a particular category makes a difference to a particular number. So for example, these are types of questions. For example, you may be interested in how, e.g., does Does acid treatment make a difference to strength? I have no idea what I might treat with acid or what strength even means. I'm just making up random words. So the idea is that the acid treatment is, well, yes or no. You either have it or you don't. That's my category. And strength would be measured in some sort of number. And so I'm interested in how the acid treatment makes a difference to the number. That's an idea of how a question that you might ask and that you might use statistics to answer. Okay? Good. And almost every question that you might ask in a data context can be represented in this sort of way. Okay. So it may also be that you just want to know more about a specific number. Okay, so e.g., what is the what is the diameter of the balls produced by my factory? The quality control sort of setting. So quality control comes up a lot with statistics. You're trying to make sure that the processes that you design and the objects that those processes produce are of good quality, and sometimes it's the size. And so you might know, what's the diameter of ball produced by my factory? And normally you'll go, well, actually, what is the mean diameter? Okay? That's a good question. You might want to know that. And this is a question about a single variable. I'm not caring at the moment what it is that affects the diameter of the ball that my factory produces. I'm only interested in the number at the moment. At some point I'll probably record some other stuff and see what causes that to be different, but at the moment I just want to know what the number is. And pretty much all statistical questions are of these two flavours. If you do more statistics in the future, you'll start to have multiple things affecting a single outcome. So a whole lot of arrows pointing at an outcome, but at the moment it's either just one variable by itself or two variables related to each other. Every question you've asked there is, on this list is of that type. So what I'm going to do is I'm going to describe which of these go with which of those. But there's one more thing that we might want to know about, which is repeated measurements or not. So sometimes when you set up one of these experiments where you collect data, or just set up a situation where you collect data, you have repeated measurements on the same objects. And that makes a difference to the type of statistics you can do. So okay, so imagine in time we have some sort of objects. This is the Barbie doll. It makes me happy to think that some of you will be one day designing Barbies. Because when I buy Barbies for my daughters, I look at it and go, look at this articulated knee. That's awesome. Someone had to design that, and that would be an engineer. So it makes me happy to think that some of you will one day be doing that, because, you know, who wouldn't want to do that? So the Barbie doll, and at some point I figure out the angle that's supposed to be produced, and then later on I figure out the angle that the knee can produce later. Again, after something happens, possibly after a certain amount of trial playing with the knee, just to see if they can make it go backwards. And I measure it twice. So this is time here. So these three bits of information, the types of variables, and the types of questions, and the repeated measurements, they are the things that go together to decide which thing to do when. There's a few other nuances as well, and I'll get to them as we go, but they're the big things. And these decide between things even that you haven't been told about. So in the future, if you ever want to learn about a statistical procedure, don't go to Wikipedia because it's crap for statistics, but go to somewhere else and ask and see if you can figure out what types of variables it works on, how the variables are arranged in the question, and whether it works on repeated measurements or not. And that should help you to at least get a handle on whether you're allowed to use it or not. just for future reference, because at some point you may say in fourth year have to do statistics, and you may need to choose to do methods that you haven't been taught yet. Okay, I'm going to run on this list. So this list, let me look at this. This list makes an attempt to talk about the context. Okay? And that context, well, if you look at that context, it's all like theoretical statistics context. What you need is context. Like what question is it attempting to answer? So we really need to add an extra column to that so that we can tell. Okay, so suppose you wanted to... Yep, just making sure I've got the list down pat. So I'm going to go through various contexts and say what goes with them there. All right, let's see. So what if you wanted to know about a single variable? And you just wanted to know about the mean of that variable. All right, that's not a question, it's a statement. I want to know about the mean. And the question you're going to ask is the mean equal to a certain number? You know, I would like my balls to have a diameter of about, I don't know, 40 centimetres. Is the mean diameter 40 centimetres? Okay, so equal to this number. That's the question I'm going to ask. Is the mean equal to this number? Cool. If you want to answer that question, then you need a bit more information, because you need to know how variable the data is. And so there's two different situations that I haven't covered on that list there, because that's the big picture. This is some nuanced details. There are two situations you may be interested in. One, where you previously have figured out what the variability of this is, and you know how variable the balls are, and you're assuming it's the same as it was before. Or you don't know and you're just going to estimate that from the data. And that's the difference between those first two columns there. I want to know a mean, and is that? All right. I want to know a mean, and I know how variable it is. I know what the standard deviation is. Or I want to know a mean, and I don't know how variable the standard. I don't know what the standard deviation is. And if you're in an exam, the clue is they'll tell you what the standard deviation is if you know it. Okay? So that's this situation here. So if I know the standard deviation or the variance, then I'm going to do a certain thing which is going to involve a z-test. But if I don't know the standard deviation, I'm going to do a t-test. And both of these tests, these are my first, this is row 1 and row 2. Both of these tests have the same structure for the calculation I do. And the calculation is always estimate minus parameter divided by standard error. And that's why they've given you those things there, because I can get that from the table. So in my z-test, maybe I'll have, is the mean equal to 40? Now I ask mean equals 40 as a question. In your statistics things, they normally call that the null hypothesis, and the null hypothesis is that it is 40. Because there's only one way to be 40, and mathematically it's easier to be 40 than not, because there's infinitely many ways to not be 40. And so that's what I would do. I would go mu equals h naught mu equals 40. So is the mean 40? Then I will do, my z will be my parameter, my estimate minus my parameter over my standard error. Or they call it SE in the table. So when I look up my table, my z will be the estimate, which is x bar, minus the parameter, which is 40, divided by the standard error, which is sigma on root n. And that's what I've looked up in my table. I can get those numbers from that. On the other hand, if I was doing a t-test, it's called a t-test because it comes out to have an answer t. And I would go estimate minus parameter divided by standard error as seen in the table. And my table has an S on root n for that one. There you go. Now here's a question. How did I know that that was a Z, you ask? Well, let me show you. Look closely at that table at the last column and tell me what you notice, someone. Reference distribution, yep. And do you notice anything else about the reference distributions? Yep.
One's the standard normal.
Yep. One's the standard normal and the other ones aren't, and the other ones are T's. That's how you tell. All the standard normals are Z's, and the other ones are T's, because they're T's. So, yeah. If it's a T, the test statistic is a T. If it's an N, the test statistic is a Z. So this one, it'll be Z equals. This one, it'll be Z equals, Z equals, Z equals, Z equals. These ones will be T equalses because they're T's. If you do other statistics, then there will be other distributions. There will be F's and chi-squareds and U's. There are other letters, but N01 is the Z distribution. I don't know why Z. It's probably German. That's why Z is. That's why the Z for the integers is a Z, because it's from German. This is my very stupid way of remembering that. Ready? It's pretty bad. See this Z? It's an N if it's this way. There you go. That's my way of remembering it. Beautiful. Okay, so the calculation you do is always estimate minus parameter divided by standard error. And I do that for every one of them. And I calculate that calculation, and then I look up to see where that number lies in my normal or T distribution. But I have to, so if it's a Z, there's only one Z distribution. But if it's a T, there's more than one T distribution. You have to tell it which one it is. And that's what this number down the bottom here is. This is what they call the degrees of freedom. There. Like that. Degrees of freedom comes from the multivariable geometry interpretation of statistics. And you don't really need to know that. I call it DF for distribution finder. There's a whole list of T distributions. There's one for each sample size. Well, not necessarily sample size, but there's one for each different situation. And you need to know which one to go up to. And in different situations, you'll go up to a different one. I mean, that's really all I wanted to say about this at the moment. And you can come and talk to us in the Maths Learning Centre about it if you want, though I prefer if you sat just on the other side of the ropes, just outside the Maths Learning Centre. I'll mark a couple of extra tables next week because I don't want you to crowd out the first years who need me more than you, just to be fair, because you wouldn't have wanted them to crowd out you last year when you were them. So, yes. Or earlier than that, depending on how long you've been here for. So all of them are that flavour, and they go with different situations. So the next one, let's look at the next one. 2 independent samples. Well, that's this situation. Does this yes or no thing of having a treatment or not having a treatment, or having a machine and another machine, or having a group of people or another group of people, or having a location or another location. That's a good one. They use that in science and ecology a lot. Two different ways of distinguishing between things and a numerical outcome on them. That's something that you might want to investigate. Okay? So does this yes or no thing make a difference to this numerical outcome? So when you read some of the exam questions, you can tell which of those they are. And there are two different things that might happen in the way that you set up the data. You might put objects under both of those situations and measure them twice. Or you may have a whole group of objects in one situation and a whole different group of objects in another situation. And that's this repeated measurements question. So I would imagine that if I had a situation, I would draw a picture of how the time order of events happened. So if you have an object and it gets split into groups, a group for category A and a group for category B, and then you measure the outcome, okay? Your objects are split into two groups, and then you measure the outcome later, and every object's only got one outcome. It's not repeated measurements, every object's just got one. That is the independent samples they're referring to. So this is split into groups. And those are the independent samples we're interested in. If it's that situation, then that's your two independent samples row. This is row 3 in your table. And again, you will calculate the difference between the two sample means and compare it to 0 and divide by the standard error, and that's what you'll do. On the other hand, if this is the time order of events, here we are in situation A and we've measured the outcome, and here we are in situation B and we've measured the outcome again on the same objects. This is row 4. So I imagine what it is like to be an object in my experiment. Okay, so if I'm one of these balls, I'll go, well, I don't exist yet, I'll run through my factory and the factory produces me, and then I get measured my diameter. Okay, and that would be this situation here. I would be produced by a different machine. Or it could be that one, there's a classic one that used to be in the assignments about these bits of fabric that are washed with different substances, and they measure the whiteness afterwards. But each fabric is cut in half and is measured with both. So that's, again, we've got the one piece of fabric has been measured under situation A and measured again under situation B. And so that's this one here. So each situation, if you imagine what it is like to be the object in that experiment and say, have I been measured twice, even if I had to be cut in half to do it, then I'm in this one here. And that's the paired comparisons, they've called it. Okay, just how to tell the difference between them. Still working on that. It's been a good 10 years of me trying to figure out how to explain that to people, and I'm sure I've got another 10 years to go before I get it really good, but that's where I'm up to with that. Okay, so far we have single numerical outcomes, and we want to know more about the mean, and that splits into two different situations. We have a yes or no treatment and a numerical outcome, and there's two different ways that I could set up that experiment too. And they've got 4 rows in our table. The next 4 rows in the table are not about numerical outcomes. The next 4 rows in the table are about categorical outcomes. Yes or no? Okay, so what if I had something happening and I did something and I went, well, did it break or not break, for example? Or did it survive this process or not survive? Or was it greater than the cutoff limit for what I was supposed to be or less than the cutoff limit? Those are the sorts of questions that we could be asking. And the question is usually about how likely it is to get the yes answer or the no answer. So like the percentage of yes, for example. Though, of course, statisticians don't like percentages, and they will, of course, not call them percentages. They'll say the proportion of yes. What if it's that question? Okay, so I can imagine for all of you going, Okay, so did you visit the Maths Learning Centre, yes or no? What proportion of yeses there are, right? Or I could, you know, my Barbies, did my articulated knee break in this process of testing, yes or no? That's the sort of thing that I'm going to ask. And so imagine looking at when you read these things, does it describe a yes or no situation where I'm asking for a proportion of how often something happens? That's what we're interested in here. So that is what they call a binomial situation. And the binomial is referring to the binomial distribution, but also to the fact that there's two options, yes or no. Binomial, two names, that's what it means. Okay, so if you're doing a test of, here's the thing, if the question is the proportion equal to this number, that question there, that's a hypothesis test. That would be a Z test, okay? Well, it's just a test. That's a testing situation. I'm testing to see, is the answer yes or no? And that would be row, where are we up to? 1, 2, 3, 4, 5. That's the binomial, no, 6. That's row 6 in your table. It's the binomial CI, binomial test. So you're asking, is the proportion equal to this number, yes or no? And you'll get a p-value and it will say yes or no. That's what p-values are for. But if your question is the proportion, no, not is, what is the proportion? So what is the options, okay? So I've got 50% in my particular experiment. You know, what could I expect that to be if I did it again? Would it be, you know, between 40% and 60%? What actually is the proportion? I know it's not 20% because I asked my hypothesis test and it told me, but what actually is the answer? That's what confidence intervals are for. And that's row 5. The binomial CI. Whoops, sorry. Now, confidence intervals are a different thing. Hypothesis tests, anything that's a test where the question is there a relationship? Okay, so back here, this one here is there a relationship? Yes or no, and I'll do a t-test. This one here is there a relationship, you know, or is the answer zero, this answer? Could someone close the back door for me? That's just telling me that we're going to have to leave shortly. Is there a relationship at all? Then I can use the test. But if I want to know what the number is, I'm going to have to arrange it differently. My confidence interval endpoints, well, this time it will be the estimate plus or minus the statistic times the standard error. That's how you make a confidence interval. So in this case, in row 5, with my binomial test, my confidence interval endpoints will be the estimate, which is p hat, plus or minus my statistic, which is from the reference distribution, so that's a z. And you normally put a star there to say, this is my specific z I'm interested in. The critical z, they call it. And then the standard error is p0, 1 minus p0. No, that's confidence intervals of p hat, is it? Yep. On n. Yep. Cool. Now, that Z star, back in the hypothesis test, I would have got Z equals the estimate minus the parameter over the standard error, like that. And it's got all the same pieces. It's got the parameter, it's got the estimate, it's got the standard error, it's got the statistic. So does this one. Technically the endpoints is the parameter. It's got the estimate, it's got the endpoint, it's got the statistic. This Z I have to calculate from my data. Okay, I get my data and I calculate the Z, and then I look it up in the Z distribution and I see what the p-value is. This Z is the other way around. I go from the p-value I'm looking for and I figure out the Z that would have given it. So if I'm going a 95% confidence interval, what's the number? 1.96. Well done. You're supposed to be able to stimulus response that. It's like, you know, you're supposed to be able to know that number, but you can look it up. Your lecturer should be giving you the most important numbers in some sort of table somewhere, or alternatively you just know that the one for 95% is 1.96. You're supposed to remember that one. The one for 10% is 1.64, but I've done this often enough to know that one. But yeah. So if it's a 95% confidence interval, that number is 1.96, just so you know. But you can also look it up. This is where you'd go up into your MATLAB, which you don't have in the exam, and go norm inv blah blah blah, that sort of thing. What I'm trying to get here is to try to make connections between things. I'm not trying to teach you for the first time. This would be crap if I was teaching you for the first time. I'm trying to make connections between different bits of the course. And there's only two more rows left in this table. The two more rows left in this table are those last two rows for the two proportions. Well, in this case, we're interested in whether there's some situation that makes a difference to the percentage of yes or no. I could draw my arrow better, I'm sure. Okay, that's that situation. It's the same as your t-tests for your two independent samples or your paired comparisons, only instead of the outcome being a number, the outcome is a yes or no. And you count how many yeses there are in one group and how many yeses there are in the other group. Most people don't think about it that way. They just think about it as the percentage in one group and the proportion in the other group. But really it is a yes or no, and you're just ignoring all the no's. Okay, so that's the two proportions. And we can imagine that we've sort of split everything into two groups. Split groups. Oh, that is not a square. Neither is that, but it's close enough. Split into two groups and then say, you know, yeah, was it yes or not? And then I count how many yeses there are. There is such a thing as doing this in the repeated measures situation, but you haven't been taught to do that in this course. So, but there is such a thing as like a paired proportions test, which is kind of cool. So, yeah. But you haven't been taught to do that. So you can actually technically do it, because you could say, does it match before and after, or does it not match before and after, and suddenly you have a yes or no already. But this is what we're doing here, and that is the last two rows. 1, 2, 3, 4, 5, 6, 7, 8. Row 7 and 8, that is a crap ampersand in the table, is about this. Row 7 is about the confidence interval, to see how far apart those two percentages are. How far apart are those two proportions? That's what the confidence interval asks. So P1 and P2. That's what we're asking. What's the difference between them? And so you'll do your two proportions CI. But is the question just, are the proportions different? Or does A versus B make a difference? They're yes or no questions, and yes or no questions are always tests. So that's one of the key things which I didn't mention earlier, I'm sorry. If your question is a yes or no question, like are they different, is it 40, then you're doing a test, and that's what p-values are for. If your question is what is this number, then that's what confidence intervals are for. And you can have a look closely at what you're being asked to do, and it's easy to do that. Normally if they want a confidence interval, they'll tell you. That's my quick and fairly dirty distinguishing between those things. And I'm hoping that there's been a small amount of information there that was useful just from the fairly scattered version of my brain after doing, 8 hours of revision seminars today. I'm going to stop there for a second.